All right, so we are armed with the following equations, okay? It all comes down to the second law of thermodynamics. Delta S of my universe is equal to the delta S of my surroundings plus the delta S of my system. Okay, well, it seemed like it was an impossibility to find the change in entropy of the surroundings. Obviously, the direction that reactions go based on what we call spontaneity is based on the second law of thermodynamics. We are locked by this. We don't play God. All we do is understand God. Or if we're not religious, understand nothing. Okay? We just play within the rules. We can't do anything but abide by these rules. So we just understand the rules and see what factors can help us. So keeping temperature and pressure constant, what did we do the other day? We figured out that there's a way to solve for this. And look at this. We call it delta G, state function. Now we put a not here because it's based on standard conditions. And it's equal to the enthalpy that we defined under standard conditions minus T delta S, which is from standard conditions measuring the absolute entropies. Now we should all understand at this point in time, party people, that the change of entropy of the system, which I forgot to write, the change of entropy of my system is tied to the molecular, what? Molecular disorder. So these are tied together, the molecular disorder. But we got cute, keeping what? Temperature constant and pressure constant. We were able to do what? Relate the delta S of the surroundings with the what? Delta H of the reaction. And if you remember, if I'm a reaction that gives off energy, that if I'm exothermic, what does that mean? That means energy is released. That energy release is making my gas in the environment go faster, be more disordered. So the energy change from the system, or the enthalpy change, I should say, at constant pressure, the Q is the delta H. Okay, any of this changes here affects the environment. It's endothermic. Energy from the surroundings is flowing into the reaction. So the what? The environment, the surroundings is getting less disordered. So we linked these two together, and this gives us free energy. Notice something, the free energy is not always going to be the enthalpy. Sometimes it's greater than the enthalpy, sometimes it's less, based on this factor. Okay, we've talked about that. But what am I after today? Well, we said that this is a great, great, cool derivation that we have. But can we really use this? Are we ever at standard conditions? Standard conditions mean you're at 1 ATM for all your reactants. You're at 25 degrees Celsius, okay? All right, and of course you have 1 molar for all your reactants, or 1 atmosphere for your partial pressures. Not very useful. So what we did when we were last together is we derived using dilution, and we found that delta G, non-standard, which is really more important to us, equals what? Well, delta G of naught, okay, plus RT ln of Q. Now, what is Q? For the millionth time, Q represents the concentrations of the products over the reactants, and the coefficients become exponents. Solids and liquids don't apply. This came from experimental evidence that diluting a solution, a gas is a solution too, increases the entropy. Okay, it's about manipulating or dealing with this. So doing our derivation with dealing with dilution of a solution, a homogeneous solution, whether it's a gas or a solute in an aqueous environment, we've got this formula. Beautiful. Now we can deal with delta G. We're not at standard conditions. Important. Okay. But what does it tell us? Well, it gave us some insight on the state of the reactants and products at a particular time. As we can see, if I've got a lot more reactants than it was measured for delta G normally, then this expression than products, a lot more reactants than products, makes this expression small, less than 0. If it's less than 0, a natural log or a log of a number less than 0 goes negative, and this whole expression goes negative. What does that mean? Okay? Well, if this goes negative, we can see we're adding a negative value, and the delta G gets more negative. So you need to understand that if we have more reactants, okay, and I'll write it. If I have more reactants, concentration, what's it going to do? Delta G is going to get more what? More negative, more spontaneous. Why? Because lowering or increasing the R here makes this number go less than 0, less than 1, which makes this go negative, and you're adding a negative value. Negative delta G just by what? By convention, us making it happen, we made it equal to be negative by our convention, makes it more negative, more spontaneous. And the opposite is also true, okay? We're going to stay in because we're short today, except for me. If the products are larger, delta G is going to get to more what? More positive, less spontaneous, which means the what? The forward reaction isn't the pathway anymore. The reverse reaction becomes the pathway. If something becomes positive, and we're always defining the forward left to right, the reverse happens. So as this number exceeds this value becomes greater than 1. Greater than 1 gives me a positive log. This becomes a greater positive, and it overcomes this value. It's going to get less spontaneous until it becomes positive, which means the pathway for the reaction to occur happens less. But that's intuitive. If I've got more reactants, you know about Le Chatelier's principle, that means, gosh darn it, that tells me something about directionality. So if I've got a lot of reactants, a lot of products than reactants in a reaction, that means the reactants are probably going to the products are going to react with each other, go in reverse. Now, if you don't see that, this is probably the best visual here. And this is really for my other class who didn't get to see this. So this, I want you to get down. Maybe. Okay, as I try to scroll up. Touches on. Okay, so when I scroll up somehow, let's see if I can do that. It's not letting me. So when I do that, here we go. When I scroll up, let's write this. Now, here we go. Very important, right here. So we have a reaction A, and let's make it a different color. All right, so we got A going to B. All right, A going to B. Now, A going to B, all right, I'm going to put a double arrow there to remind everybody there is an opportunity for this to be reversible. If we're dealing with gases, okay, in a vessel, this is always a possibility, okay? Now, any case, what do I have here, party people? Well, listen, I'm going to put a big U right here. Now, don't draw yourself, okay? Now, what I'm going to put right in the middle is a K. This represents KEQ. Now, if you remember last year, KEQ, called the law of mass action, is what you looked upon. KEQ is equal to what? KEQ is the same thing as Q, except it's at equilibrium. It's the concentrations of the products to their respective coefficients to their exponent over the reactants over their exponents. Solids and liquids don't apply. Why? solids and liquids don't have a dilution process. Only solutions can go in here, and those could be gases as well. Gases could have molarities, brackets are molarities, parentheses or partial pressures. Both can be used. Now what does KQ tell me? If my reaction is at equilibrium, which means the forward rate equals the reverse rate, it tells me who's favored. Every single reaction has a unique point by which the reaction finds an equilibrium position. So if I had a ball and it was going back and forth, it would eventually rest at the equilibrium position. Now for chemical reactions, you have forward reactions and reverse reaction, and eventually it finds an equilibrium position. Now remember last year I did the tank demonstration with the water. And remember I was pouring water from one tank to the other with different sized cups. People thought equilibrium was when the two tank levels equaled each other. But the equilibrium is when the what? I was pouring the same amount of water into one tank into the other. And that is when you had someone favored. At every single reversible reaction where equilibrium can occur, you're going to have a position where someone's favored. I want to know that as a chemist. If I'm trying to make some products and my equilibrium position is small, what would that mean? I have a lot more what? Reactants than products. So my equilibrium position is small, and I'm trying to make some products, I have some issues, don't I? If my equilibrium position is large, meaning I have a lot more products than normal, what does that mean? That means when I mix the things together, let them achieve equilibrium, I'm going to produce some products. If my equilibrium position is small, I have some issues because if I mix them together, let them do their thing, they'll get to equilibrium and what? Have very few what? Reactants. I'm sorry, very few products. A lot of reactants and very few products. So a small KQ, and we write it because I even got confused. A small KQ, right, let's do it. KQ, if it's a large, if it's small, it means who's favored? The reactants are. Okay? And if K is big, the products are. And if my products are favored, that means you're going to go to make products. If your reactants are favored, it's going to go to make what? Reactants. We better be aware of this. How does this tie into delta G? It ties in beautifully. It's Le Chatelier's principle. Let me show you. Okay, so I have 100% of A here. Over here I have 100% B. Now what does that mean? That means that as I go down here, maybe I have 90% A, okay, and 10% B. 80% A, 10% B. So what's happening as I move this way on this position, the number of reactants is decreasing, the products are increasing. Now, I put KQ here in my drawing. KQ is never going to be 50%, 50%, but I just drew it here for simplistic cases. KQ is going to be favoring one side or the other. I have a fictitious KQ that's 50% just so we can see this. Now watch what happens. Okay, now, as I have a value of my KQ not at KQ, I have the value of this not at equilibrium. What do we call that? I have the products over reactants, coefficients become exponents, solids, liquids don't apply. I have a snapshot of the reactants and products concentrations, but I'm not at equilibrium. What's that value? Q, right. So K, Q, and Q are the same thing, except one's at equilibrium and one is not. Last year we spent most of our time dealing with equilibrium. But now I have a Q. Let's pretend my Q is at this position. My current state of my reaction is right here. Okay? So here's my Q. Now, remember, Q is the same thing. It's products over reactants. So what does that mean? Well, if my Q is over here, and this is 100% what? A? What does that mean? That means there's a lot more what than what? There's a lot more A, which is reactant. So there's a lot more A than B. And let's be crazy and put what it means. So the concentration of B over the concentration of A. Hey. So I have a lot more A than B. So Q is what? Compared to K, you think? Smaller, right. Q is smaller than K. So we would say Q is less than KEQ in this entire what? Region in front, yes? Every place I have a position for my concentrations that is in front of my KEQ, that means my Q is too small than the position it wants to achieve. Look at the drawing, guys. Where do you think this reaction is going to go? Right, it's going to fall down to find. This is going to be spontaneous where? It's going to be spontaneous in this direction. Why? Because my Q is too small. It's going to move. Everything moves toward equilibrium. So I would write delta G is what? Positive or negative? Negative in this direction. Which means in the reverse, it's positive. Does this make sense intuitively? Does it work mathematically? You bet your donkey it does. Right? If I've got too many what? If I have too much R. If I've got too much ah, as we say in New England, okay, this makes this be less than 1, okay, which makes this expression negative, which makes this what? We're adding a negative value, it lowers my delta G to become more negative. So, knowing how much Q you have compared to your KEQ tells you something about the spontaneity. You better have this position in front though, because there's some KEQs that are really small like KSPs, and it's hard to be in front. So most of the time you have the reverse reactions. Remember the crystallization, the KSPs last year? We'll get to that. Okay, so on this side, Q is larger, smaller than K. Now what if you got a scenario over here? What if we have some reactants and products? Okay, oops. Let's draw another position here. So this is a Q, and Q is equal to B to some power over A. Now, in my reaction, they had no exponents, no coefficients. So in this case, who's bigger?
B.
B is bigger. And if B is bigger, okay, Q is bigger than what? Q is bigger than
KQ.
KQ, right. Now why? I've got more products than my equilibrium position. So where is this reaction going to go? Or I have what? Too small of reactants than my equilibrium position. So where's the bouncing ball want to go? If I'm up here, where's it going to go? Yeah, it's going to go to the left. And so my friends in chemistry, we say that this direction is now favored. Delta G is what now? Positive. Because we're defining what direction. I have A going to B. It is positive for the forward direction, which means it's negative for the reverse. So we write a delta G of positive showing there is no pathway. Again, you have to understand, this is all based on the forward reaction. Yes?
How do you find like the value where it stops going either left or right, where that equilibrium?
What was our homework last night? What is the minimum amount that we need to make it spontaneous?
Oh, that equation.
Right. Remember, that was the homework? How much of the products do we need to make this become what? Small enough for the reaction to be spontaneous.
7.
Okay? To make this forward, you have to be above your Q. That's why, people, it's a great question. It's almost like I asked you to do it. That's why, okay, this works. Now, clearly, there's a link to KEQ and delta G. Let's go find it. Clearly, there's a link, right? Everyone see that? Where this position is tells us something about whether or not our reaction will be spontaneous given a set of reactants, correct? So there's got to be a link. So here comes our second to last delta G formula. Delta G, non-standard, is equal to what? Delta G standard plus RT ln of Q. Now watch. Let's see how delta K, or let's see how the equilibrium constant is linked here. We see it intuitively. Let's see if it makes sense mathematically. Now, to convert this to the K, which is the same value, isn't it? Same, but we're going to be at equilibrium. So we're going to convert that to equilibrium. Easy as pie on a Sunday afternoon. Watch. Ln of K EQ. This will be RT. This will be plus G of naught, standard conditions. But, whoa! If we're at KQ, delta G non-standard must be what? 0. This can't be 0. It's based on its condition, so that's 0. Ooh la la. Now, if it's 0, let's solve for delta G. Delta G non-standard, standard, is equal to negative RT ln of K, or KQ. Hey, there it is. So, what does KQ equal? Products over reactants. So, back to our drawing. Let's go look and see if our mathematics do what? Match our intuitiveness. So if my K, well, we'll see here. If my K is large, that means this is going to do what? Move up. If K and Q is products over reactants. I know I have Q here, but it's the same thing. So if I'm at equilibrium and my K is large, that means there's a lot more products. So I would move this dot up. As I move this dot up, what are the possibilities for Q to be less than KQ as I move this up? Greater, right. So as K is bigger, the forward direction becomes a larger negative. And you know that intuitively, but look, as K becomes bigger, products become bigger, this becomes a what? A bigger positive value. There's a negative in front. This becomes more negative as K gets bigger. And if K gets smaller, that means I'm pushing this K here. It gets really, really hard to find a Q that's going to make it spontaneous to be over here. Q's got to be less than KQ for it to go forward. So as I have more reactants, this becomes a negative number because the ln of a number less than 0 becomes negative. This becomes positive, and delta G for the forward reaction becomes positive as your KQ gets smaller. Remember, KQ is a pinpoint place where the reaction tells us where it's stable in equilibrium based on a certain temperature. Okay, now we can affect this, and this is important. You learned this last year, but on a different level. I said to you what? If I had more products than reactants, it shifts to the what? Left. If you had more what? Reactants than products, you shift to the right. If I took out the products, if I took out A, I made Q what? If I take out A as I make it, Q's getting what? Big. So now it's going to go in the reverse. If I take out A, Q gets what? Big. And the forward occurs. Let's review that. Remember this? Remember, here's the reaction party, people. Oh, too much. Watch. It go crazy. Okay. Here's my reaction. A is going to B. If I circle B and have too much A, okay, now usually it makes more sense of A plus B, because if I have A plus B, it's easy to understand. If I've got A plus B, let's pretend I'm a princess and this is a B here. If I increase the A, isn't the B, or let's make it C. Let's pretend it's A and C. Okay? So let's make that a C right here. I know I don't have it, but look, let's pretend. It's easy to think this way. If I have a lot more A, isn't A going to hit C more often than the reverse? And we learned it would go that way faster. But now we know by increasing the A, we're doing what? Make Q what? Smaller than KQ. And therefore the forward reaction goes. If I do the same thing with B, make it bigger. Okay, same idea. Making it bigger would make it the Q bigger. It would go in the reverse. All the things you learned, but now I believe a better way. Then we say, okay, take away B. Taking the B away would do what? Making the reaction what? Q smaller. And the reaction would go forward to make more B. Okay? And then we made some leaps into temperature. I'm going to talk about that right now. We're almost done. I don't even know what time's left. Okay? Let's do this. How much time do I have left?
Maybe 8 minutes.
Okay, cool. Let me review this
Not
time
really,
here.
not really sure, but that's just a guess.
5, and then we got out at 35, so out of 40. So I think you might have.
Very artistic.
10,
Okay.
15.
Yeah. I'm going to have to. So let's do this, party people. Energy gives me what? Bad Grotsky. Ah!
Oh.
I don't like this. Okay, here we go. Energy. Let's put A over here because I don't want to erase that. Plus the energy gives me B. Stay with me. Now, temperature affects KQ. KQ is temperature dependent. Last year we did this, but I can only do this because I couldn't get through all the thermal, obviously. We said, if I have an endothermic reaction, treat it like a reactant. If I add energy to it, where does it go? By adding energy to a reaction that can achieve equilibrium, or a reaction at equilibrium, what did we say?
It goes to the product.
Yeah. So a reaction at equilibrium, if you increase the energy level, what you're saying, party people, the reaction would shift. And what we learn is, hey, increase the energy of an endothermic reaction, treat it as a reactant to understand it, but the rule was increasing the energy of an endothermic reaction favors the endothermic way always. Now you can use that. And if you go look at the reverse reaction, which is exothermic, all right, lowering the energy favors the exothermic way. Remember that? All right. Now, if we have this scenario, remember this from last, maybe we didn't do this last year, but here we go. Let's do this. Let's go to the next page. All right, I have this formula. N, oops, I want to do that color. Bad Grotsky, good pizza again. Let's get rid of that. Let's go to blue. I have N2O, 2 of them, make this. N2O4. Let's call it dimer. Okay, they're right here. They're right here. Now, N2O is that brown gas that we get when we oxidize like the copper. All right? N2O4 is a clear gas. So these are at equilibrium. It's hard to say who's favored because, well, it's darker. The dark always outshines the lightness, so you can't look at that. So this is an ampule of N2O2 and mixed with NO2 at equilibrium. So I need what? Double arrow. Okay, so let's do that. Now, I can figure out where the energy goes. Is it a forward endothermic or is it a forward exothermic? Well, here's an ice bath. Let one sit in it. I'm going to take the heat away. The reaction's going to shift where? Well, we don't know. But when we take the heat away, we favor the exo or the endothermic problem of a reaction. Exo, you take the heat away, reaction's going to what? Shift to make more heat. That was the rule that we learned. Le Chatelier's principle, you add a stress to reaction equilibrium, it does what? It undoes that stress by doing the opposite. Yes, Matt?
Shouldn't it be NO2?
No, it can be any, NO2, thank you. Thank you. Why don't you speak sooner? Because I didn't allow you to. NO2, thank you. Okay, now. If you look, sitting in the ice bath, all right, it's getting lighter. Now for those that I should write, let's sit in there for a little longer. The clear is the N2O4. And the one that's brown, okay, has the brown. Okay, so clearly, by putting this in an ice bath, it's getting lighter. Now, if you don't believe me, let's take a hot bath. Hopefully, I'll drop this. Okay, and I need another tube. Okay. So put this in a hot bath. Here I'm adding energy. Equilibrium is temperature dependent. So if I add energy, I'm favoring which way here? Le Chatelier's principle states, if you remember, add a stress to a reaction, it shifts to undo the stress. The stress is I'm adding too much heat. So it's going to favor the endo. That's what you learned. And clearly it got what? Darker in the bottom. So I'm favoring the NO2 when I what? Add heat. And I'm favoring the N2O4 when I take away heat. Where does the energy go? When I added heat, I'm going this way. When I take away heat. So which way? Surroundings. Where does the energy go? The reaction shifted. It seemed like it shifted this way to the clear when I took what? When I took energy away. When I take energy away, it shifted. It seemed like it shifted. Okay? I'll explain in a second. So if it's going clear, when I'm adding what? Ice, aren't I favoring the exothermic way? Does this make sense? I take the heat away, the reaction shifts to make more heat, as we learned last year. And if that is true, if I add more heat, it's going to shift to lower the heat to go this way. Does that make sense? So we just found where the heat is in this reaction. But the point is, there's no shifting here. We created a brand new equilibrium position. These are brand new equilibrium positions. These are not shifting. K did what for this one? K moved. Remember my circle? K did what? K is now over here. And then for, we'll call this K2. And then the K for this one was what? Shifted where? To the brown. K is temperature dependent. Can we prove it mathematically? You bet your donkey, let's do it. Now you have to know, guys, for this course, what I just stated, which is something we did last year, but I want you to see it with some mathematics and we're done. So watch. Delta G naught is equal to delta S minus T, delta H minus T delta S. And then we have another expression. Delta G that we just found is equal to what? Minus RT ln of K, EQ. Set them equal to each other. Delta H minus T delta S equals negative RT ln of K. Everybody with me so far? Just I can make them equal to each other. They're the same thing. Now I'm going to solve for ln of K. Watch what I do here. Negative RT over here. Negative RT over here. Okay, that's all I'm doing. Look what cancels. Temperature. So what do I have? Change in H naught over negative RT plus, right, delta S over A equals K, ln of K, EQ. Now what does this mean, party people? We're almost done. If I have an endothermic reaction, right? What do we say? If I have an endothermic reaction, what's going to happen? It's going to shift where? Only when I do what? Add heat. Okay, so stay with me. If I have an endothermic reaction, what's the charge for delta H? Watch, don't stop writing. This is what charge? This is positive, right? Yeah. So if delta H is positive, I can do another ink maybe. Here we go. Increasing the temperature will do what? Increasing the temperature will, this is a positive value, isn't it? So this is a negative value. Increasing the temperature makes this negative, it makes it smaller. Increasing this temperature makes the denominator bigger, but it makes the overall expression a smaller negative, which means it's not as what? Spontaneous in the forward. This being a smaller negative means what? Smaller negative means that the reaction is not going to do what? A smaller negative means you're not going to be as spontaneous in the forward direction. If I add heat, it shifted the what? The endothermic way. If it's shifting this way, it's not as what? Spontaneous. So that is showing me that right there.